Mars colonization is humanity's most expensive suicide mission. The domed cities, the terraformed dreams, the backup plan for humanity. It's fantasy, not distant future fantasy. Forget everything you've heard about Mars colonies. And here is a question for you. If you could bring only one item from Earth to help you survive on Mars, what would it be? Let me know in the comments. I'll pin the most creative answer. Now let's begin. Let's talk about radiation. This is the silent killer that nobody wants to discuss when painting rosy pictures of Martian colonies. Here on Earth, we live protected beneath an invisible shield, a magnetic cocoon that deflects the most dangerous particles the universe hurls at us. Mars has no such protection. Earth's magnetic field extends thousands of kilometers into space, forming what scientists call the magnetosphere. This protective bubble deflects charged particles streaming from the sun, particles that would otherwise bombard our planet's surface with lethal doses of radiation. Mars lost its global magnetic field roughly 4 billion years ago, when a planet's core cools and stops generating the churning, electrically conductive currents that produce magnetism. That shield vanishes. Mars has only small patches of localized magnetic fields in its southern hemisphere, remnants of an ancient global field, but these provide virtually no planetary protection. Without this magnetic shield, Mars stands naked against two primary sources of radiation: solar particle events and galactic cosmic rays. Solar particle events occur when the Sun releases massive bursts of energetic particles during solar flares and coronal mass ejections. These events can deliver radiation doses that would be immediately harmful to unprotected humans. During a major solar particle event, an astronaut on the Martian surface could receive a lethal radiation dose within hours if not properly sheltered. Galactic cosmic rays present an even more insidious threat. These are high-energy particles, primarily protons and atomic nuclei, that originate from supernova explosions and other violent cosmic events far beyond our solar system. They travel at nearly the speed of light and carry enormous energies. Unlike solar radiation, which comes in sporadic bursts, galactic cosmic rays provide a constant, unrelenting stream of radiation exposure. Recent data from NASA's Radiation Assessment Detector aboard the Curiosity rover has given us precise measurements of the radiation environment on Mars. The findings are sobering. An astronaut on the Martian surface would be exposed to approximately 0.66 sieverts of radiation during a round trip to Mars, including the journey and a 500-day stay on the surface. To put this in perspective, the annual radiation dose limit for radiation workers on Earth is 50 millisieverts. The Mars mission dose is more than 10 times that amount, but these numbers only tell part of the story. The biological effects of cosmic radiation differ fundamentally from the radiation we're familiar with on Earth. When a high-energy cosmic ray particle strikes human tissue, it doesn't just damage the cells it directly impacts. It creates a track of ionization, ripping electrons from atoms and molecules along its path. This creates cascades of secondary particles and chemical reactions that can damage DNA, proteins, and cellular structures throughout a much larger volume of tissue than the particle itself traveled through. The health consequences are severe and varied. Increased cancer risk is the most obvious concern. Studies of atomic bomb survivors, radiation workers, and medical patients exposed to radiation have established clear dose-response relationships between radiation exposure and cancer incidence. The type of radiation found in space, particularly heavy ions from galactic cosmic rays, is more effective at causing cancer than the gamma rays and X-rays we typically study on Earth. Cardiovascular disease represents another major concern that has emerged from recent research. Studies of astronauts who traveled beyond Earth's protective magnetic field during the Apollo missions show elevated rates of cardiovascular mortality compared to astronauts who never left low Earth orbit. Animal studies using particle beams that simulate cosmic radiation have demonstrated that this radiation can damage blood vessels, promote atherosclerosis, and impair cardiovascular function. Perhaps most troubling are the effects on the central nervous system. Research conducted over the past decade has revealed that cosmic radiation can cause cognitive impairment, memory problems, anxiety, and depression. Studies exposing mice to simulated cosmic radiation have shown damage to neurons, reduction in dendritic complexity, and impairment of learning and memory. These effects occurred at radiation doses equivalent to what astronauts would experience during a Mars mission. The timing of these cognitive effects is particularly concerning. Unlike cancer, which might not develop for years or decades after exposure, some cognitive impacts appear relatively quickly. Imagine colonists arriving on Mars after a 6 to 9 month journey, already experiencing cognitive impairment that affects their decision-making, reaction times, and ability to handle complex tasks. In an environment where a single mistake could be fatal, these cognitive effects could prove catastrophic. Shielding against this radiation presents enormous engineering challenges. On Earth, we're protected by an atmosphere equivalent to about 10 meters of water in terms of shielding effectiveness. Mars' thin atmosphere provides protection equivalent to only about 20 centimeters of water. To achieve Earth-like protection, Martian habitats would need extraordinarily thick walls. Traditional shielding materials like lead, which work well against gamma rays, are actually less effective against cosmic radiation. When high-energy particles strike heavy atoms in materials like lead, they can create secondary radiation through a process called spallation, potentially making the radiation environment inside a habitat worse than outside. The most effective shielding uses hydrogen-rich materials like water or polyethylene, which slow down and absorb energetic particles without producing as much secondary radiation. A habitat providing adequate radiation protection would require walls several meters thick of water or equivalent shielding material. Consider the implications. Every kilogram of material on Mars comes at an enormous cost, either transported from Earth at costs of thousands of dollars per kilogram, or manufactured on Mars from local resources using energy-intensive processes. Building habitats with multi-meter thick walls for even a small settlement would require moving millions of tons of material. Some proposals suggest using Martian regolith, the loose soil and rock covering the surface, as shielding material. Piling regolith over habitats could provide radiation protection without transporting material from Earth. However, this creates its own challenges. Regolith must be moved, probably by autonomous machinery. The weight of regolith creates structural loads that habitats must support. Regolith-covered habitats would be partially or fully underground, complicating construction, limiting natural light, and creating psychological challenges for inhabitants. If you're finding this information valuable, please consider subscribing to the channel and giving this video a thumbs up. It really helps spread this scientific perspective to more people. Alternative approaches to radiation protection have been proposed, but each faces significant hurdles. Some scientists have suggested creating an artificial magnetic field for Mars, either through a satellite positioned at Mars L, one Lagrange point, or through ground-based systems. In 2021, researchers published detailed engineering studies exploring how such a system might work. The concept involves generating a powerful magnetic field that would deflect solar wind and some cosmic radiation, similar to Earth's magnetosphere. The challenges are staggering. Creating a magnetic field strong enough to protect an entire planet would require enormous amounts of energy, likely hundreds of terawatts, sustained continuously. This vastly exceeds the total power generation capacity of human civilization on Earth. The infrastructure needed to generate, maintain, and power such a field would represent a mega engineering project beyond anything humanity has attempted. While theoretically possible according to the laws of physics, the practical barriers place this firmly in the realm of far future speculation rather than near-term possibility. Pharmaceutical countermeasures represent another avenue of research. Scientists are investigating drugs that might reduce radiation damage by scavenging free radicals, enhancing DNA repair mechanisms, or protecting particularly vulnerable tissues. Some promising compounds have shown effectiveness in animal studies. However, these medications would need to be taken continuously throughout the mission, potentially for years or decades. The long-term effects of such medications are unknown. They might reduce radiation damage but create other health problems. Moreover, no pharmaceutical intervention can completely eliminate radiation risk. Even optimistic projections suggest drugs might reduce cancer risk by perhaps 20 to 30%, still leaving colonists with radiation exposures far exceeding safe limits. The concept of spending time underground in lava tubes or caves has gained traction as a potential solution to radiation exposure. Mars, like Earth, experienced extensive volcanic activity in its past. This volcanism created networks of underground caverns where lava once flowed, but has since drained away, leaving hollow tubes beneath the surface. These natural structures could provide ready-made radiation shelters, protected by meters or even tens of meters of rock overhead. Orbital imagery from spacecraft like Mars Reconnaissance Orbiter has identified numerous potential lava tube entrances, particularly in volcanic regions like the Tharsis Plateau. Some of these tubes appear enormous, potentially large enough to house entire settlements. The rock overhead would provide excellent radiation shielding without requiring the construction of massive artificial structures. However, living underground comes with profound challenges. Humans evolved under open skies with natural light cycles that regulate our circadian rhythms, our hormone production, our sleep patterns, and our psychological well-being. Studies of people living in extreme environments like Antarctic research stations and submarines show that isolation, confinement, and lack of natural light create significant psychological stress even over periods of months. Imagine spending years, or potentially your entire life, in underground caverns, never seeing open sky, never feeling wind, never experiencing the psychological benefits of natural landscapes. The physiological effects of living without natural sunlight would be significant. Vitamin D production requires ultraviolet light exposure. While this could be supplemented through diet or artificial UV exposure, it represents just one of many biological rhythms tied to natural light cycles. Studies have shown that artificial lighting, no matter how carefully designed, doesn't fully replicate the benefits of natural sunlight for human health and psychology. Beyond radiation, we must confront the reality of Martian soil composition. This isn't just dirt that happens to be on another planet. Martian regolith contains compounds that are actively toxic to life as we know it. The Phoenix lander in 2008 and the Curiosity rover in subsequent years detected significant concentrations of perchlorates throughout Martian soil. Perchlorates are chemical compounds containing chlorine and oxygen that act as powerful oxidizers. On Earth, perchlorates are used in rocket fuel, fireworks, and explosives precisely because of their oxidizing properties. They're also known to be toxic to humans, interfering with thyroid function even at low concentrations. The thyroid gland regulates metabolism, growth, and development. Perchlorate exposure can cause hypothyroidism, developmental delays in children, and various metabolic disorders. The concentrations detected on Mars are not trivial. Measurements show perchlorate levels ranging from 0.4 to 0.6% by weight in soil samples. That's 4,000 to 6,000 parts per million. To put this in context, the Environmental Protection Agency's drinking water standard for perchlorate on Earth is 15 parts per billion. The Martian soil contains perchlorate concentrations hundreds of thousands of times higher than what we consider safe in drinking water. This creates cascading problems for any settlement. Agriculture would be impossible in native Martian soil without extensive treatment. The perchlorates would need to be removed before plants could safely grow, And even then, ensuring complete removal would be critical since any remaining perchlorates would concentrate in edible crops. Water extracted from Martian ice would likely contain dissolved perchlorates and would require purification before use. NASA researchers have been working on biological methods to remove perchlorates using specially engineered bacteria. These microorganisms can metabolize perchlorates, breaking them down into harmless chloride and oxygen. In 2024, scientists published research on perchlorate-reducing bacteria that could potentially be used to detoxify Martian water and soil. The bacteria engineered from terrestrial species show promise in laboratory settings. However, scaling this from laboratory experiments to industrial processes capable of treating thousands of tons of soil and millions of liters of water presents enormous challenges. The bacteria would need controlled environments, nutrients, time to process materials, and systems to separate them from treated soil or water. Every step adds complexity, energy requirements, and potential failure points to an already precarious life support system. Speaking of water, let's examine one of the most fundamental requirements for human survival. We need water for drinking, food preparation, hygiene, agriculture, and industrial processes. An average person on Earth consumes roughly 3 liters of water per day for drinking alone. Including all uses, per capita water consumption in developed nations ranges from 200 to 600 liters per day. Even with aggressive recycling and conservation, a Martian colony would need substantial water resources. Mars does contain water, primarily in the form of subsurface ice. Orbital observations and surface measurements have confirmed extensive ice deposits, particularly at higher latitudes. The Phoenix lander directly sampled water ice just beneath the surface near the North Polar region. Radar instruments on orbiting spacecraft have detected what appear to be massive ice deposits buried under layers of dust and rock. But accessing this ice and converting it to usable water requires enormous energy expenditure. The ice is frozen solid at temperatures reaching -125 degrees Celsius in polar regions. Extracting it requires either excavating large quantities of frozen regolith or drilling into subsurface ice deposits. The ice must then be melted, requiring approximately 334 joules per gram just to convert ice at 0 degrees Celsius to liquid water, plus additional energy to warm the ice from Martian temperatures to the melting point. I actually created another video exploring what happened to Mars's water and atmosphere over billions of years. If you want to understand how Mars transformed from a potentially habitable world to the desert planet we see today, check out my video on the card above. The link is in the description as well. Understanding Mars' past helps us appreciate why colonizing it is so challenging. Once extracted and melted, the water needs purification to remove perchlorates and other contaminants. It must be stored in heated tanks to prevent refreezing. Distribution systems would need to be maintained in a pressurized, temperature-controlled state. Every pipe, valve, and container becomes a potential failure point where water could freeze, rupture containment, and be lost to the thin Martian atmosphere. Water recycling would be absolutely critical. The International Space Station recycles approximately 93% of water, converting urine, sweat, and even moisture from breath back into drinking water. A Martian colony would need to achieve similar or better recycling efficiency. However, even with excellent recycling, some water would inevitably be lost through various processes, requiring continuous extraction of new water from Martian ice. The energy requirements for all these processes are staggering. Every human activity on Mars would require energy, heating habitats against the frigid cold, maintaining atmospheric pressure, recycling air and water, growing food, manufacturing materials, processing regolith, charging vehicles and equipment, running communication systems, and providing light during the long Martian nights. Solar power seems like an obvious choice, Mars receives sunlight, and solar panels require no fuel. However, Mars receives less than half the solar energy that Earth does. Dust storms, which can engulf the entire planet for weeks or months, further reduce solar power generation. The Opportunity rover, which operated on Mars for nearly 15 years, was finally defeated by a global dust storm in 2018 that blocked sunlight from its solar panels. Nuclear power offers an alternative. NASA has developed small nuclear reactors designed for space applications, like the Kilo Power Project, which demonstrated a 10-kilowatt reactor prototype. Nuclear power provides consistent output regardless of day-night cycles or dust storms. However, a settlement would need multiple reactors to provide adequate power, along with all the associated safety systems, cooling mechanisms, and nuclear fuel that would need to be transported from Earth or eventually manufactured on Mars. Every energy system on Mars would face harsh environmental conditions. Solar panels would accumulate dust, reducing efficiency. Temperature extremes would stress all components. Radiation would degrade materials over time. Maintenance would be constant, and replacement parts would be scarce, making redundancy essential but expensive. Food production represents another fundamental challenge that is often glossed over in optimistic colonization scenarios. Humans need roughly 2,000 calories per day, plus essential nutrients, vitamins, and minerals. A colony of even 100 people would need to produce approximately 73 million calories per year, equivalent to what roughly 20 hectares of farmland produce on Earth under favorable conditions. Growing food on Mars means doing so in controlled environments. There's no possibility of open-air agriculture in the toxic, near-vacuum, radiation-bathed Martian environment. Every plant would need to grow in pressurized, heated, lit, and atmospherically controlled greenhouses or underground facilities. The energy costs for lighting alone would be immense, as plants require specific wavelengths and intensities of light for photosynthesis. Research on growing plants in Martian regolith simulants has shown mixed results. Some studies have successfully grown plants in soil mixtures containing simulated Martian regolith, but only after removing or neutralizing the perchlorates and adding substantial organic matter and nutrients. The regolith itself is essentially sterile mineral powder, lacking the organic content, beneficial microorganisms, and complex chemistry that make Earth soil fertile. Experiments conducted in controlled environment agriculture here on Earth demonstrate that growing enough food for one person requires approximately 40 to 50 square meters of growing space under optimized hydroponic or aeroponic conditions, plus significant infrastructure for water delivery, nutrient management, lighting, and climate control. Scaling this to even a small colony would require facilities of thousands of square meters, all of which would need to be constructed, pressurized, heated, lit, and maintained. The psychological and social dimensions of Mars colonization are often overlooked in technical discussions, but they may prove just as challenging as the engineering problems. Space agencies have studied the psychological effects of isolation and confinement extensively through analog missions where volunteers spend extended periods in simulated space habitats in isolated locations on Earth. These studies consistently reveal significant psychological stresses. Interpersonal conflicts arise even among carefully selected, highly trained individuals. The monotony of limited environments creates boredom and depression. The inability to leave, to experience nature, or to have privacy creates chronic stress. Communication delays with Earth would range from 3 to 22 minutes one way, depending on the planet's positions, making real-time conversation impossible and creating a sense of profound isolation. The Mars 500 experiment, conducted from 2010 to 2011, confined 6 volunteers in a simulated spacecraft for 520 days to study the psychological effects of a Mars mission. Participants experienced sleep disorders, mood changes, decreased activity levels, and interpersonal tensions despite being on Earth with the knowledge they could leave in an emergency. A real Mars mission would offer no such escape option. The selection of colonists would face extraordinary challenges. Who goes to Mars? What criteria determine suitability? Age becomes a critical factor when considering radiation exposure and the long-term health effects. Younger individuals would face decades of increased cancer risk, while older colonists might not possess the physical resilience needed for the harsh environment. The question of sending families versus only adults opens ethical dimensions that society has barely begun to address. Consider the implications of pregnancy and child development on Mars. No human has ever been conceived, gestated, or born beyond Earth's gravity and protective magnetic field. We have essentially no data on how fetal development would proceed under Martian conditions. Animal studies in microgravity have shown concerning effects on development, including skeletal abnormalities, balance system problems, and cardiovascular issues. While Mars has more gravity than orbital environments, it's still only 38% of Earth's pull. The radiation exposure during pregnancy would be particularly concerning. Developing fetuses are far more sensitive to radiation than adults. The rapidly dividing cells during embryonic and fetal development are precisely the cells most vulnerable to radiation damage. Radiation exposure during pregnancy increases risks of birth defects, developmental delays, and childhood cancers. The constant background radiation on Mars would expose every pregnancy to risks that would be considered completely unacceptable on Earth. Children growing up in Martian gravity would develop bones and muscles adapted to that environment. Their cardiovascular systems would calibrate themselves to the lower gravitational load. Their balance and coordination would develop in that reduced gravity field. The crucial question becomes, could these children ever return to Earth? Would their bodies, developed entirely in Martian conditions, be able to function in Earth's stronger gravity? We genuinely don't know, but the physiological principles suggest that returning to Earth might be extremely difficult or even impossible for individuals who spent their developmental years on Mars. This creates a troubling scenario where Martian colonization might become a one-way trip, not just for the original settlers, but for their children and all subsequent generations. Born on Mars, adapted to Mars, potentially unable to survive Earth's environment, these individuals would be truly Martian in a biological sense. Whether this represents expansion of human civilization or creation of a genetically isolated population facing inevitable extinction is a question we must seriously consider. The medical infrastructure required for a Martian colony presents challenges that dwarf anything we've attempted in remote Earth locations. Every medical condition that can be treated on Earth through our vast network of specialists, facilities, and equipment would need to be addressed with whatever resources exist locally on Mars. There would be no medical evacuations, no calling in specialists, no transferring patients to better equipped facilities. A colonist suffering a heart attack, stroke, severe infection, traumatic injury, or any of thousands of potential medical emergencies would need to be treated entirely with local resources. This means the colony would need surgical capabilities, diagnostic equipment, medications, blood supplies, and medical expertise, covering essentially all fields of medicine. The International Space Station, despite having highly trained crew members and good medical supplies, is designed with the assumption that medical emergencies can result in evacuation to Earth within hours if necessary. Mars offers no such option. Pharmaceutical supplies present their own challenge. Medications have limited shelf lives, often measured in months or a few years. A Mars colony would need to either stockpile enormous quantities of medications, receiving regular resupply from Earth, or develop the capability to manufacture pharmaceuticals locally. Pharmaceutical manufacturing is an extraordinarily complex process requiring precise chemical synthesis, quality control, sterile conditions for injectable medications, and expertise spanning organic chemistry, biochemistry, and pharmacology. the same challenges apply to medical equipment. Diagnostic devices, surgical instruments, monitoring equipment, and life support systems all require maintenance, calibration, and eventual replacement. Many modern medical devices rely on complex electronics, precision optics, or sterile disposable components. Manufacturing replacements on Mars would require establishing industrial capabilities that took Earth centuries to develop. Dental care provides a specific example that illustrates the broader challenges. Tooth decay, gum disease, and dental trauma are common human health issues. On Earth, we address these through regular preventive care and interventional procedures when necessary. A Mars colony would need dental equipment, materials for fillings and crowns, capability for extractions and more complex procedures, and individuals trained in dentistry. A severe dental infection, if left untreated, can spread to the bloodstream and become life-threatening. Something as mundane as a toothache becomes a serious concern when you're 200 million kilometers from the nearest dentist. Mental health care would be equally critical. The psychological stresses of isolation, confinement, danger, and separation from Earth would inevitably create mental health challenges. Depression, anxiety, trauma responses, and potentially more severe psychiatric conditions would need to be addressed. This requires not just medications, but trained mental health professionals and therapeutic approaches adapted to the unique Martian context. Let's examine the logistics of supply from Earth, because no Mars colony would be truly self-sufficient for decades at minimum. Every kilogram of cargo sent to Mars requires a launch from Earth, a months-long journey through interplanetary space, and a landing on Mars. Current costs for launching payloads to low Earth orbit run several $1,000s per kilogram, even with reusable rockets. Sending that same kilogram to Mars increases costs by at least an order of magnitude. The timing of supply missions is constrained by orbital mechanics. Earth and Mars align favorably for efficient transfer trajectories roughly every 26 months during what's called a launch window. Miss that window, and you wait over 2 years for the next one. This means supply missions must be planned years in advance, and any urgent need that arises between launch windows cannot be addressed quickly. Transit time from Earth to Mars ranges from 6 to 9 months, depending on the specific trajectory chosen. This delay means that even during a launch window, colonists would wait half a year or more for supplies to arrive after launch. Combined with the 2-year spacing between launch windows, Mars colonists could potentially face waits of up to 2.5 years between when a need is identified and when a supply shipment addressing that need arrives. The mass requirements for even a small colony are staggering. Published studies of Mars settlement logistics estimate that establishing and maintaining a colony of 100 people would require delivering hundreds of tons of cargo annually. This includes food supplements, replacement parts, new equipment, medical supplies, and all the consumables that cannot yet be produced on Mars. At current launch costs, even with optimistic projections for reusable rocket technology, the annual cost of supplying such a colony would measure in the billions of dollars. Economic viability represents perhaps the most fundamental question about Mars colonization. What economic activity on Mars could justify the enormous costs of establishing and maintaining a settlement? On Earth, colonization throughout history has been driven by economic motives: access to resources, new agricultural land, trade routes, or strategic positioning. What does Mars offer that could generate economic returns? The most commonly cited answer is scientific research. Mars is indeed a fascinating subject for scientific study, particularly regarding questions about past life, planetary evolution, and comparative planetology. However, scientific research has never generated the kind of economic returns that would justify trillion-dollar investments in colonization infrastructure. Science is funded because societies value knowledge, not because it offers financial profits. Mining resources on Mars for export to Earth makes no economic sense when you examine the numbers. The cost of transporting materials from Mars to Earth would be so high that virtually nothing could be valuable enough to justify it. Precious metals, rare earth elements, or any physical commodity would cost far more to ship from Mars than it would sell for on Earth, even assuming unlimited demand. Some proposals suggest Mars could serve as a staging point for asteroid mining operations or deeper space exploration. However, this logic is circular. Why stage from Mars when launching from Earth or constructing facilities in orbit would be far more efficient? Mars' gravity, well, though smaller than Earth's, still requires significant energy to escape. Its distance from Earth creates communication delays and logistical complications. There's no obvious operational advantage to using Mars as a base for space operations compared to alternatives. Tourism has been proposed as a potential economic driver. Wealthy individuals might pay enormous sums for the experience of visiting Mars. However, tourism requires infrastructure for relatively brief visits and is fundamentally different from colonization. Moreover, the extreme dangers and hardships of Mars travel would limit the potential market to a tiny number of individuals willing to risk their lives for the experience. The concept of Mars as a backup for humanity in case of catastrophic events on Earth is often invoked, but this argument doesn't withstand scrutiny. Any catastrophe on Earth severe enough to make our planet less habitable than Mars would have to be truly apocalyptic. Nuclear war, asteroid impact, climate change, pandemics, or any combination of disasters would still leave Earth with breathable atmosphere, liquid water, protection from radiation, and viable ecosystems. Even a severely damaged Earth would be orders of magnitude more hospitable than pristine Mars. Furthermore, a Mars colony would depend entirely on Earth for survival for the foreseeable future. If some catastrophe disrupted Earth's ability to send supply missions, the Mars colony would perish within years at most. The idea that Mars represents insurance against human extinction only makes sense if the colony becomes truly self-sufficient, and we've seen how extraordinarily difficult that would be to achieve. Technological self-sufficiency would require replicating on Mars essentially the entire industrial and technological infrastructure of Earth civilization. Think about everything required to build a computer chip: specialized chemicals, ultra-pure materials, precision manufacturing equipment, clean rooms, energy systems, and expertise spanning multiple scientific and engineering disciplines. Now consider that this represents just one tiny subset of modern technology. A self-sufficient Mars colony would need to manufacture everything from simple tools to complex electronics, from basic chemicals to advanced medications, from textiles to construction materials. It would need to mine raw materials, refine them into pure elements and compounds, synthesize everything that cannot be mined, and manufacture finished goods. The industrial base required encompasses essentially the entire spectrum of human technological capability. On Earth, this industrial capacity developed over millennia and now spans the entire globe. Modern manufacturing relies on complex supply chains that source materials and components from dozens of countries. Rare earth elements come from specific geological deposits. Specialized manufacturing capabilities exist in concentrated locations. The interconnected nature of global industry means that no single nation, much less a small colony, possesses complete technological self-sufficiency. Replicating this on Mars would require not just transporting equipment, but establishing mining operations, chemical plants, manufacturing facilities, power generation sufficient for industrial processes, and a population with the necessary expertise. Studies attempting to estimate the minimum viable population for a self-sufficient Mars colony typically arrive at numbers in the thousands to tens of thousands of people, each requiring life support, habitat space, food, water, and all the infrastructure we've discussed. The timeline for achieving even partial self-sufficiency stretches across decades. Initial missions would establish basic infrastructure and conduct preliminary resource extraction. Subsequent missions would expand capabilities incrementally. Manufacturing would begin with simple items and slowly increase in sophistication as infrastructure develops. Optimistic timelines suggest that partial self-sufficiency might be achievable within 30 to 50 years of the first permanent settlement, but these timelines assume everything proceeds smoothly, funding continues uninterrupted, and no major setbacks occur. History suggests that reality rarely matches optimistic projections. The International Space Station took over a decade longer to complete than initially planned and cost more than double the original estimates. Space shuttle development exceeded budgets and timelines significantly. These projects occurred in low Earth orbit, just a few hundred kilometers from Earth, with continuous support from the ground. Mars is orders of magnitude more challenging. The concept of terraforming Mars has captured imaginations for generations. The idea is seductive. Rather than living in sealed habitats, what if we could transform Mars itself into an Earth-like world with breathable atmosphere, liquid water on the surface, and habitable temperatures? If achievable, terraforming would solve nearly all the challenges we've discussed. Unfortunately, the scientific reality suggests that terraforming Mars may be fundamentally impossible with any technology we can currently envision. Let's start with the most basic requirement: atmospheric pressure. As we discussed earlier, Mars currently has an atmospheric pressure of roughly 610 pascals, less than 1% of Earth's. To support liquid water and eventually human life, Mars would need an atmospheric pressure of at least 6,000 pascals, and ideally closer to Earth's 100,000 pascals. This means increasing the total mass of the Martian atmosphere by a factor of 10 to 100. Where would this atmosphere come from? The most commonly proposed source is carbon dioxide locked in Martian polar ice caps and absorbed in surface rocks. In 2018, researchers from the University of Colorado Boulder published a comprehensive study in Nature Astronomy examining the total inventory of accessible carbon dioxide on Mars. Their findings were sobering. The study concluded that even if we released all the carbon dioxide from the polar caps and all the carbon dioxide that could be liberated from rocks through heating, we could increase Mars' atmospheric pressure by only about 10 to 20 millibars. That's roughly 3% of Earth's atmospheric pressure, not nearly enough to support liquid water stability or provide meaningful radiation protection. The study examined decades of spacecraft data measuring the composition and thickness of polar ice, the distribution of carbon-bearing minerals, and the total inventory of volatiles that could potentially be released. The implications are profound. The most accessible reservoir of potential atmospheric gases on Mars is simply insufficient for terraforming, even if we could release all of it. Some proposals suggest importing volatiles from elsewhere in the solar system, perhaps by redirecting comets or asteroids to impact Mars and deliver water and atmospheric gases. However, the scale of this undertaking beggars imagination. To increase Mars' atmospheric mass by a factor of 100 would require delivering roughly 50 quadrillion tons of material. For comparison, the total mass of all humans on Earth is approximately 500 million tons. The entire mass of all human-made objects on Earth is estimated at around 30 trillion tons. We would need to deliver material to Mars equivalent to over 1,000 times the total mass of everything humanity has ever built, and do so across interplanetary distances. Even if we solve the material sourcing problem through some revolutionary technology, we face an even more fundamental barrier: atmospheric retention. Mars lost its original thick atmosphere over billions of years, and it lost it for reasons that still exist today. Without a global magnetic field, the solar wind strips atmospheric gases away through a process called atmospheric sputtering. Charged particles in the solar wind interact with atoms and molecules in the upper atmosphere, transferring energy and momentum. Some atmospheric particles gain enough energy to escape Mars' weak gravity entirely. This process operates continuously, and measurements from NASA's MAVEN spacecraft have quantified the current atmospheric loss rate at approximately 100 tons per day. This might sound small compared to the total atmospheric mass, but over geological timescales, it's devastating. If we somehow created a thick atmosphere on Mars, the same processes that stripped the original atmosphere would begin removing the new one. Calculations suggest that without a protective magnetic field, Mars would lose a significant fraction of any artificially created atmosphere over timescales of tens of millions of years. That might seem like a long time, but it means the terraforming would not be permanent. It would require continuous replenishment of atmospheric gases, essentially maintaining the atmosphere artificially forever. The idea of creating an artificial magnetic field for Mars has been seriously studied. In 2017, NASA scientists presented a concept at the Planetary Science Vision 2050 workshop. The proposal involved positioning a magnetic dipole shield at Mars' L1 Lagrange point, the location between Mars and the Sun where gravitational forces balance. This shield would generate a magnetic field strong enough to deflect the solar wind around Mars, creating an artificial magnetosphere. Computer simulations of this concept showed that such a shield could potentially reduce atmospheric loss and allow atmospheric pressure to gradually increase through outgassing from the surface. However, the engineering challenges are immense. The magnetic field would need to be generated by a structure measuring thousands of kilometers across, powered by energy sources delivering tens to hundreds of terawatts continuously. The infrastructure would need to operate autonomously for centuries, maintaining precise positioning and withstanding the harsh space environment. More recent studies published in 2025 and 2026 have explored various approaches to creating artificial magnetospheres, including ground-based systems that would generate magnetic fields directly from Mars's surface. These studies conclude that while not physically impossible, the energy requirements and engineering complexity place such systems far beyond current technological capabilities, likely remaining impractical for centuries even under optimistic assumptions about technological progress. Let's assume for the sake of argument that we somehow solve the atmospheric mass and retention problems. We still face the challenge of atmospheric composition. An atmosphere of carbon dioxide, even at Earth-like pressure, wouldn't be breathable. Humans need oxygen, ideally at partial pressures between 15 and 30 kilopascals, which corresponds to oxygen concentrations of 15 to 30% in an Earth pressure atmosphere. Creating breathable oxygen would require photosynthetic organisms, probably engineered microbes or plants capable of surviving Martian conditions. These organisms would need to convert carbon dioxide to oxygen through photosynthesis, gradually transforming the atmospheric composition over time. However, the timescales involved are staggering. On Earth, photosynthetic organisms took approximately 2 billion years to convert our early carbon dioxide-rich atmosphere to an oxygen-rich one. Even with optimized engineered organisms and ideal conditions, estimates for oxygenating Mars range from thousands to millions of years. During this entire period, the surface would remain uninhabitable without life support, and maintaining the photosynthetic biosphere would require managing planetary ecosystems on a scale humanity has never attempted. The energy requirements for terraforming represent another fundamental barrier. Warming Mars to temperatures where liquid water is stable requires adding substantial energy to the planet's climate system. Proposals range from building orbital mirrors to reflect additional sunlight onto Mars, to releasing powerful greenhouse gases into the atmosphere, to covering portions of the surface with dark material to reduce albedo and increase solar heat absorption. Each approach faces severe limitations. Orbital mirrors large enough to meaningfully warm Mars would need to be hundreds or thousands of kilometers across. Manufacturing such structures, even from lightweight materials, would require resources exceeding anything humanity has produced. Positioning and maintaining them in stable orbits while withstanding solar radiation pressure would demand continuous active control. Greenhouse gases could theoretically warm Mars more efficiently than carbon dioxide. Proposals have suggested manufacturing chlorofluorocarbons or other super greenhouse gases on Mars and releasing them into the atmosphere. Research published in Nature Astronomy in 2025 examined this approach in detail. The study calculated that producing sufficient quantities of super greenhouse gases to warm Mars by even 20 to 30 degrees Celsius would require industrial facilities operating at scales comparable to Earth's entire chemical industry, sustained for centuries, consuming vast amounts of energy and raw materials. Moreover, these greenhouse gases would need continuous replenishment. Many break down under ultraviolet radiation, which is intense on Mars due to the thin atmosphere and lack of an ozone layer. The production facilities would need to operate indefinitely, making this not a one-time terraforming project, but a permanent planetary life support system requiring constant energy input and maintenance. The soil chemistry problems we discussed earlier would persist even in a terraformed Mars. The perchlorates throughout Martian regolith wouldn't disappear just because we added atmosphere. Before the surface could support Earth-like ecosystems, we would need to either remove the perchlorates from vast areas or create completely new soil using imported or synthesized organic material. The scale of soil remediation required for even small habitable zones would involve processing billions of tons of material. Temperature management presents additional challenges. Even with a thicker atmosphere and greenhouse warming, Mars would remain colder than Earth due to its greater distance from the Sun. Mars receives only 43% as much solar energy per unit area as Earth does. No amount of atmospheric engineering can change this fundamental orbital reality. Mars could potentially be warmed to temperatures where liquid water is stable, perhaps achieving average temperatures around the freezing point, but it would never naturally match Earth's climate without truly massive ongoing energy inputs. The latest research in terraforming science, published in early 2026 in the European Physical Journal Plus, provides a comprehensive assessment of radiation risks and environmental modification strategies. The authors conclude that even under optimistic scenarios where atmospheric pressure is increased and some magnetic shielding is achieved, radiation exposure on a terraformed Mars would remain significantly higher than on Earth. The combination of higher cosmic ray flux and reduced atmospheric shielding compared to Earth means that cancer risks and other radiation health effects would persist even in the best-case terraforming scenarios. A 2026 paper posted to R-Kutov by researchers at the University of Chicago examined the mass, energy, and industrial throughput constraints for Mars terraforming. Their analysis is particularly revealing. They calculated that achieving breathable oxygen levels would require processing atmospheric mass on the exaton scale. That's 10 to the 18th power kilograms. The minimum oxygenation work would exceed 10 to the 25th joules, requiring sustained industrial power output in the hundreds of terawatts to petawatt range, maintained for centuries to millennia. To put these numbers in perspective, total human civilization on Earth currently consumes approximately 18 terawatts of power across all uses: electricity generation, transportation, heating, industrial processes, everything. Terraforming Mars would require building an industrial infrastructure on Mars that matches or exceeds Earth's total power generation, then sustaining it for centuries, all while supporting a human population in an extremely hostile environment. The authors of the study conclude that regional habitability improvements through what they call paraterraforming, essentially building large enclosed habitable areas, might be achievable on near-term industrial scales. However, global transformation of Mars into an Earth-like planet would require multi-century planetary industrial efforts, and becomes credible only if we discover much larger volatile inventories than currently known or developed means to import massive quantities of material from elsewhere in the solar system. Recent studies on plant growth in simulated Martian conditions provide additional sobering data. Research published in Scientific Reports in 2026 examined how maize plants respond to combinations of Martian gravity, hypomagnetic fields, and Mars global simulant regolith. The findings showed that while reduced gravity and weak magnetic fields created specific stress responses in plants, the chemical composition of Martian regolith emerged as the dominant stressor, overwhelming the plant's ability to adapt. The study found that the combination of reduced gravity and toxic regolith produced systemic stress responses that severely impaired plant growth and survival. Even after accounting for perchlorate removal, the regolith's mineralogy and chemistry created challenges for plant development that would require extensive soil modification or complete replacement with artificially created growing media. The political and governance challenges of Mars colonization receive far less attention than the technical obstacles, yet they may prove equally insurmountable. Who governs a Mars colony? Under what legal framework? What happens when conflicts arise between colonists and Earth authorities, or between different factions within the colony itself? The Outer Space Treaty of 1967, which remains the foundational document of international space law, states that celestial bodies cannot be claimed by any nation through sovereignty, use, or occupation. This creates immediate legal ambiguities for colonization. If no nation can claim Mars, under whose jurisdiction do colonists live? What laws apply? Who enforces them? Some legal scholars argue that while nations cannot claim territory, private entities or individuals might establish property rights through use and development. However, this interpretation remains contested, and no international consensus exists. The legal frameworks that would govern resource extraction, land use, criminal justice, civil disputes, and governance structures on Mars are essentially undefined. Imagine a scenario where a dispute arises between colonists, perhaps over resource allocation or personal conflicts. On Earth, we have established legal systems with courts, law enforcement, and clear jurisdictional boundaries. On Mars, who investigates crimes? Who serves as judge and jury? What punishments can be imposed when imprisonment in a small colony creates logistical nightmares and execution is ethically problematic? The communication delay between Earth and Mars creates practical governance challenges. When Mars and Earth are at their farthest separation, radio signals take approximately 22 minutes to travel one way. This means any question posed to Earth authorities would receive a response at minimum 44 minutes later, and often much longer when you account for deliberation time. Real-time governance from Earth becomes impossible. This delay necessitates local decision-making authority, but it also creates opportunities for divergence between Earth and Mars societies. Colonists living in radically different conditions, facing unique challenges and separated by hundreds of millions of kilometers, would inevitably develop distinct perspectives, values, and priorities. History shows that colonies separated from parent civilizations by far shorter distances and shorter communication times have frequently sought independence. The question of reproduction and population control on Mars raises profound ethical issues. In an environment where every additional person requires substantial life support resources and increases risks for the entire community, can colonists freely choose to have children? Would population limits be imposed? Who decides such intimate personal matters? And how would such policies be enforced? The genetic implications of a small founding population create additional concerns. Population genetics tells us that small, isolated populations face genetic drift, inbreeding, and loss of genetic diversity. These effects can become pronounced over just a few generations. A Mars colony starting with even hundreds of carefully selected individuals would represent a severe genetic bottleneck compared to Earth's billions. Over generations, this could lead to increased prevalence of genetic disorders and reduced genetic diversity. Some proposals suggest using reproductive technologies like sperm and egg banks or even genetic engineering to maintain genetic diversity and health in Martian populations. However, this ventures into ethically fraught territory involving designer babies, eugenics concerns, and fundamental questions about reproductive autonomy and human dignity. The psychological concept of the third-generation problem deserves serious consideration. The first generation of Mars colonists would be volunteers who chose to go, highly motivated individuals who believe in the mission. The second generation, their children, would grow up knowing Earth only through videos and stories, but they might still feel connected to humanity's homeworld. The third generation would be entirely Martian, born to Mars-born parents, with no direct connection to Earth. Studies of isolated communities on Earth show that third generations often experience identity crises and social tensions as the founding mission loses its immediacy and becomes historical rather than personal. On Mars, this could manifest as resentment toward the hardships imposed by living in an environment fundamentally hostile to human life, questioning why they should continue sacrificing for a mission they never chose. The economics of Mars colonization extend beyond simple cost calculations to questions of financial sustainability over the decades or centuries required to establish self-sufficiency. Who funds the ongoing operations? Private companies would require profits or at least credible paths to future profitability. Governments funding through taxation must justify expenditures to populations facing pressing needs on Earth. Current estimates for establishing even a small research outpost on Mars range from hundreds of billions to trillions of dollars depending on the scope and timeline. The Mars Society's estimates for a 100-person settlement using relatively optimistic assumptions about technology development and cost reductions still arrive at figures exceeding $100 billion just for initial establishment, not including ongoing operational costs. For comparison, the International Space Station, humanity's most expensive single project, cost approximately $150 billion over several decades of construction and has required billions more for annual operations. The ISS operates in low Earth orbit just 400 kilometers from Earth, with continuous support and crew rotation every few months. Mars is orders of magnitude more challenging. The Apollo program, humanity's most ambitious space achievement to date, cost approximately $280 billion in current dollars. It sent 12 humans to the Moon's surface for a combined total of less than 300 hours and returned them safely to Earth. The program was sustained for only a few years during a unique historical moment of Cold War competition and economic prosperity. Sustaining funding for Mars colonization would require commitment spanning decades without the geopolitical drivers that motivated Apollo. Historical patterns of exploration and colonization on Earth provide instructive but ultimately problematic parallels. European colonization of the Americas, Australia, and other regions was driven by access to resources that could be extracted and returned to sponsor nations, by agricultural opportunities in new lands, and by geopolitical competition for strategic territories. None of these drivers apply to Mars. The Americas offered gold, silver, furs, timber, and eventually agricultural products that could be shipped back to Europe at profit. Australia provided agricultural land and eventually mineral wealth. These economic returns justified the costs and risks of transoceanic voyages. Mars offers no comparable economic incentives under current or foreseeable technology. Some commentators draw parallels between Mars colonization and Antarctic research stations, suggesting that Mars colonies could operate similarly as government-funded research outposts. However, Antarctic stations serve specific scientific purposes, can be resupplied easily, and personnel rotate every few months to a year. The logistics of Antarctic operations, while challenging, are trivial compared to Mars. Ships and aircraft travel to Antarctica regularly. Costs are measured in millions, not billions. The sunk cost fallacy represents a psychological trap that could affect Mars colonization programs. Once enormous resources have been invested in establishing initial infrastructure, political and psychological pressures would mount to continue the program, even if it becomes clear that original goals are unattainable. The desire to justify past expenditures could drive continued investment in a fundamentally unsustainable endeavor. We see this pattern in large infrastructure projects on Earth that exceed budgets and fail to deliver promised benefits, but continue receiving funding because stopping would mean admitting failure. For Mars colonization, this could result in decades of continued expenditure supporting an outpost that can never become self-sufficient, essentially creating a permanent welfare dependent on Earth support. The opportunity cost of Mars colonization deserves serious consideration. The hundreds of billions or trillions of dollars required for colonization could alternatively address pressing challenges on Earth or pursue other space objectives with clearer benefits. Climate change mitigation, renewable energy development, disease eradication, poverty reduction, or even robotic exploration of the solar system could potentially deliver greater benefits for humanity at lower cost and risk. Robotic missions to Mars have proven extraordinarily successful at conducting scientific research. The Curiosity and Perseverance rovers, the InSight lander, and orbiting spacecraft have revolutionized our understanding of Martian geology, climate history, and potential for past life. These missions cost billions rather than trillions and risk no human lives. As robotic technology advances with improvements in artificial intelligence, remote operation, and autonomous decision-making, the scientific case for human presence on Mars becomes weaker rather than stronger. Recent advances in machine learning and robotics, demonstrated by systems here on Earth, suggest that within decades, robotic systems might match or exceed human capabilities for scientific exploration while requiring only a fraction of the life support infrastructure. A robotic research station could operate in exposed surface conditions, work continuously without sleep or shifts, never require food or water, and conduct dangerous experiments without ethical concerns. The philosophical question of whether Mars colonization is desirable even if it becomes technically feasible deserves consideration. Some environmental ethicists argue that we have no right to contaminate Mars with Earth life or transform its environment to suit our needs. While Mars appears sterile as far as current evidence shows, the possibility of indigenous Martian life, perhaps in subsurface environments we haven't yet sampled, cannot be completely ruled out. Planetary protection protocols exist specifically to prevent contaminating Mars with Earth organisms and to protect any potential Martian life from disruption by our missions. These protocols require extensive sterilization of spacecraft and careful contamination control. Human colonization would make meaningful planetary protection impossible. Humans carry trillions of microorganisms. Our presence would inevitably introduce Earth life to Mars. If Mars does harbor indigenous life, even microbial life in subsurface aquifers or other protected niches, human colonization could cause its extinction before we even discover it. The scientific and philosophical value of potential Martian life, representing a second independent origin of biology, would be immeasurable. Some argue that preserving Mars in its current state for scientific study should take precedence over colonization ambitions. The transhumanist perspective offers a different angle on Mars colonization challenges. Rather than trying to make Mars suitable for current human biology, perhaps we should modify humans to survive Martian conditions. Genetic engineering, cybernetic enhancements, or other modifications could potentially create humans better adapted to high radiation, low pressure, reduced gravity, and other Martian conditions. However, this approach raises profound ethical questions about human identity and the acceptable boundaries of biological modification. At what point do modifications become so extensive that the resulting beings are no longer human in any meaningful sense? Who consents to such modifications, especially for children who would be engineered before birth? These questions venture into bioethics territory that society has barely begun to address. The technological dependencies of a Mars colony create cascading vulnerabilities that become clearer when we examine specific systems in detail. Consider the pressurized habitats where colonists would live. These structures must maintain internal pressure roughly 100 times greater than the external Martian atmosphere. This pressure differential creates enormous structural stresses. On Earth, we build pressurized structures like aircraft fuselages and submarines, but these operate under vastly different conditions. Aircraft experience pressure differentials of roughly 50 to 80 kilopascals during flight, less than the 100 kilopascal differential required on Mars. More importantly, aircraft failures typically allow for emergency landings within minutes. Submarines can surface. A habitat breach on Mars offers no such escape options. The materials required for Martian habitats must simultaneously be strong enough to contain pressure, light enough to transport from Earth or manufacture locally, resistant to temperature extremes ranging from -125 to +20 degrees Celsius, resistant to abrasion from wind-blown dust, and resistant to degradation from ultraviolet radiation. They must maintain these properties for decades without failure because replacement would be extraordinarily difficult. Inflatable habitat concepts, like those being developed by companies such as Sierra Space, offer advantages in transportability. These structures can be launched in compact form and expanded upon deployment. However, inflatable habitats rely on flexible materials that are more vulnerable to puncture and degradation than rigid structures. The redundancy required to ensure safety multiplies mass and complexity. Rigid metal or composite structures offer greater protection but require more mass to achieve equivalent volume. Manufacturing such structures on Mars would require establishing metalworking or advanced composite manufacturing capabilities, complete with all the necessary industrial infrastructure. Transporting prefabricated structures from Earth confronts the harsh realities of launch costs and payload limitations. Every seal, joint, valve, and penetration in the habitat pressure envelope represents a potential failure point. Windows, if included, must withstand not just the pressure differential, but also temperature cycling and radiation exposure without developing leaks or structural weaknesses. The complexity multiplies when you consider airlocks for entry and exit, life support system connections, power line penetrations, and communication antenna mounts. Maintenance requirements for these systems would be constant. Seals degrade over time, particularly under temperature extremes and radiation exposure. Structural fatigue develops from pressure cycling. Dust infiltration damages mechanisms. A habitat maintenance program would require extensive spare parts, specialized tools, diagnostic equipment, and personnel with appropriate expertise. The redundancy necessary for safety creates its own challenges. Best practices for life-critical systems require at least triple redundancy, meaning 3 independent systems capable of performing each critical function. For a Mars habitat, this means multiple independent air supplies, multiple power systems, multiple thermal control systems, and multiple pressure vessels or compartmentalized sections that can be isolated if one fails. This redundancy multiplies the mass, volume, power consumption, and maintenance requirements of the colony infrastructure. It also increases the number of potential failure modes. More systems mean more components that can fail, more interfaces between systems that must be maintained, and more complexity that must be managed by the colonists. The atmospheric composition inside habitats requires careful control. Humans need oxygen, but pure oxygen atmospheres are dangerous due to fire risks. The Apollo 1 tragedy in 1967, where 3 astronauts died in a cabin fire during a ground test, demonstrated the extreme flammability of materials in pure oxygen at elevated pressure. Mars habitats would likely use nitrogen-oxygen mixtures similar to Earth's atmosphere. However, nitrogen must either be transported from Earth or extracted from Martian sources. Mars' atmosphere contains about 2.7% nitrogen, so extraction is theoretically possible but requires processing enormous volumes of thin Martian atmosphere to obtain useful quantities. The equipment for this extraction, compression, purification, and storage adds to the colony's industrial requirements. Carbon dioxide removal from habitat atmospheres presents an ongoing challenge. Humans exhale carbon dioxide, and concentrations above 1,000 parts per million cause cognitive impairment. At 5,000 parts per million, exposure over 8 hours causes headaches and lethargy. Higher concentrations become rapidly dangerous. The ISS uses a combination of chemical carbon dioxide scrubbers and regenerative systems to maintain atmospheric quality. Chemical scrubbers like lithium hydroxide effectively remove carbon dioxide but are consumable, meaning they must be regularly replaced. Regenerative systems can recycle scrubbing materials but require energy, maintenance, and eventual replacement parts. Either approach adds to the colony's resource requirements and creates dependencies on supply chains or local manufacturing. Temperature control in Martian habitats involves managing both internal heat generation and external temperature extremes. Human bodies, electronics, lighting, and machinery all generate heat that must be dissipated. On Earth, we do this through air conditioning systems that ultimately reject heat to the external environment. On Mars, the thin atmosphere provides minimal heat transfer capability. Radiative heat rejection works in the Martian environment but requires large radiator surfaces that must be kept free of dust, protected from damage, and actively cooled with circulating fluids. These radiators become additional external components vulnerable to failure. During Martian winter or nighttime periods, the challenge reverses. Preventing excessive heat loss from habitats into the frigid environment requires excellent insulation and active heating systems. The thermal cycling between Martian day and night creates mechanical stresses on all components. Materials expand when heated and contract when cooled. Different materials expand at different rates. Over thousands of cycles, these expansion and contraction differences create fatigue in joints, seals, and connections. Managing thermal expansion and contraction represents a significant engineering challenge for any long-duration surface infrastructure. Power generation and storage on Mars merit deeper examination because energy underlies every other system. Solar power on Mars faces the reduced solar flux we mentioned earlier, but also the challenge of dust accumulation on panels. The Opportunity and Spirit rovers both experienced significant power reductions from dust buildup on their solar panels, though fortunately, occasional wind events would sometimes clean the panels partially. A fixed solar installation cannot rely on fortunate wind patterns to maintain efficiency. Dust storms can reduce solar power generation by 90% or more for weeks or months. The global dust storm of 2018, which ended Opportunity's mission, blocked so much sunlight that it appeared similar to night for weeks. A solar-dependent colony would need energy storage capacity sufficient to survive such events. Battery technology, even with advances in recent years, struggles to provide the energy density and longevity required. The largest grid-scale battery installations on Earth provide storage measured in hundreds of megawatt-hours, enough to power communities for hours or at most a few days. Storing enough energy to sustain a Mars colony through weeks or months of reduced solar input would require battery banks of enormous mass and volume. Battery performance degrades in extreme cold, and Martian nighttime temperatures would freeze most battery chemistries solid without active heating. Heating batteries consumes energy, creating a parasitic loss that reduces overall system efficiency. The cycle life of batteries, the number of charge-discharge cycles they can undergo before significant capacity degradation, limits their useful lifespan to perhaps a few years under harsh Martian conditions. Nuclear power offers an alternative that provides consistent output regardless of dust storms or day-night cycles. NASA's Kilo Power project demonstrated a 10-kilowatt fission reactor prototype designed for space applications. Scaling up to colony requirements would need multiple such units or larger reactor designs delivering hundreds of kilowatts to megawatts. Nuclear reactors require cooling systems to remove waste heat, fuel that either comes from Earth or must be processed from Martian uranium deposits if they exist in accessible forms, radiation shielding to protect colonists, and highly trained personnel for operation and maintenance. The nuclear fuel cycle involves some of the most complex industrial processes humanity has developed. Spent nuclear fuel must be stored safely, and while radiation shielding is less critical on Mars where background radiation is already high, preventing contamination of water supplies or habitable areas remains important. The long-term waste management challenges that plague nuclear power on Earth would transfer to Mars with the added complexity of the hostile environment. Geothermal power, which provides significant energy on Earth in volcanically active regions, seems unlikely on Mars. While Mars experienced extensive volcanism in its past, the planet appears geologically dead today, with no evidence of current volcanic activity or accessible geothermal gradients that could be exploited for power generation. Wind power faces the challenge of Mars' thin atmosphere. Wind power generation depends on atmospheric density as well as wind speed. The thin Martian atmosphere means that even very high wind speeds carry little kinetic energy. Calculations show that wind turbines on Mars would need to be enormous and spin at very high speeds to generate meaningful power, creating engineering challenges with blade materials and bearing systems. The energy storage problem extends beyond just electrical power. Chemical feedstocks for manufacturing, fuel for vehicles, and buffer stocks of consumables all represent forms of stored energy and resources that a colony would need to maintain. The total mass of stored resources required for safety margins multiplies quickly when you account for all the different systems and materials involved. Food production energy requirements deserve specific attention. Plants require light for photosynthesis, and on Mars, all food production would occur in controlled environments with artificial lighting. Photosynthetically active radiation, the wavelengths plants use, must be delivered at sufficient intensity and for sufficient duration each day to support plant growth. Published studies on controlled environment agriculture show that producing 1 kilogram of edible plant material requires approximately 15 to 20 kilowatt hours of electrical energy for lighting alone, not including climate control, water circulation, and monitoring systems. A colony of 100 people consuming 2,000 calories per day would need roughly 250 kilograms of food daily, requiring approximately 4,000 kilowatt hours just for agricultural lighting. This energy consumption, sustained continuously, represents a base load of roughly 170 kilowatts for food production alone. Add the power required for habitat climate control, life support, water processing, manufacturing, charging vehicles and equipment, communications and all other systems, and the total power requirement for even a small colony reaches into the megawatt range. For perspective, 1 megawatt of continuous power generation would require either approximately 4,000 square meters of solar panels on Mars under optimal conditions without dust, or several kilopower-scale nuclear reactors. The infrastructure to generate, distribute, and manage this much power represents a significant fraction of the colony's total mass and complexity. Water recycling efficiency becomes critical when we examine the actual performance of existing systems. The ISS water recovery system achieves approximately 93% recovery, meaning 7% of water is lost through various processes and must be replaced. This seems impressive until you calculate the implications for a Mars colony. If each colonist uses even a conservative 50 liters of water per day, 100 colonists would cycle 5,000 liters daily. At 7% loss, that's 350 liters per day that must be replaced. Over a year, this totals nearly 130,000 liters, or 130 metric tons of water that must be extracted from Martian ice, melted, and purified annually. Extracting this much water from subsurface ice requires mining operations on a substantial scale. The ice must be excavated, transported to processing facilities, melted, purified to remove perchlorates and other contaminants, and distributed to storage and use points. All these processes consume energy and require equipment that must be maintained or replaced. If you made this far, I am sure you will love this other video at the left side of the screen. This one problem makes returning from Mars impossible. We've been sold a fantasy of Mars colonies and interplanetary civilization, but the physics of bringing astronauts home alive is a nightmare we aren't talking about enough. See you there.